APIs act as a bridge between two programs. So it's important to understand the philosophy behind PyMAPDL if we hope to build reliable and insightful Python engineering apps with the MAPDL solver. In this video, we'll discuss how APDL commands are implemented and used in the Python environment, what are the advantages of calling MAPDL Pythonically, how to obtain output from PyMAPDL. Finally, we'll set up and solve a simple 2D plane strain model in PyMAPDL and execute it in batch to automate mesh convergence study. Let's get started. The PyMAPDL commands are Pythonic statements that act as a wrapper for APDL commands. When these commands are issued in Python, PyMAPDL passes them to the MAPDL instance, executes the command, and returns the output to Python. Each APDL command has been translated to the Python format where APDL arguments are passed as keyword arguments. For instance, the APDL command ecell, s, type, 1 is translated to mapdl.ecell s, type, vmin equals to 1 in PyMAPDL. Unlike APDL, in PyMAPDL, one must issue full command name and not just the first 4 characters. For example, mapdl.aglu is not recognized. Instead, use mapdl.aglu. It's also important to note that PyMAPDL commands are Pythonic statements. Therefore, they are case sensitive. APDL commands that start with / and star have those characters removed. Here, prep7 is written as mapdl.prep7 and *get is written as mapdl.get. In cases where removing a / or star will cause a conflict with other commands, such as in solu and /solu and vget and *vget, a prefix / or star is added to the Pythonic statement. For example, solu is written as mapdl.solu and /solu is written as mapdl./solu. Similarly, vget and *vget are translated to mapdl.vget and mapdl.*vget. At any given time, one can issue help mapdl.command name in the Python terminal to pull up the command reference. When it comes to post-processing, there's a special class, ansys.mapdl.core.post.postprocessing, implemented in PyMAPDL. While both post1 and post26 APDL commands are supported in PyMAPDL, it may be advantageous to use this class in the Python environment. For instance, one can extract data from results directly to NumPy arrays for further processing. PyMAPDL also provides a way of translating existing APDL commands into Pythonic format using convert_script. One can also convert a block of APDL commands using convert_APDL_block. PyMAPDL allows us to integrate APDL in a true programming environment with a powerful ecosystem. Pythonic data types can be passed as both arguments and parameters to APDL, so integration with other Pythonic modules is easier. We can also iterate over a range, strings, lists, etc. using loops in Python. In addition to this, we can set up a FE model as a callable function, so it can be automated or integrated into engineering workflows. This can be very helpful in developing vertical apps and in design optimization workflows. Since the whole program is developed using Python statements, one can use pep8, which is a style guide for Python codes, and write beautiful and readable codes, making it easy to maintain and distribute to wider users. When we call MAPDL from Python, the MAPDL program is running in the background, and one can access the solver output dynamically within Python. The solver output can either be printed to screen or written to a separate text file using these commands. Since Python and MAPDL are both executing different sets of commands, errors and warnings may arise from both the programs. In PyMAPDL, all errors and warnings are handled Pythonically. When errors are encountered, a traceback is provided, indicating which line in the code triggered it. If the error arises from MAPDL, then the corresponding error message is also provided. Warnings arising from MAPDL are also handled Pythonically. An important situation to note, however, is the default PyMAPDL behavior when a command is ignored. For instance, if a command is issued under the wrong processor, MAPDL ignores the command and issues a warning. But this is treated as an error in PyMAPDL and immediately kills the instance. Fortunately, this behavior can be changed by setting mapdl.allow_ignore equals to true if needed. So please keep this in mind when developing programs. Most MAPDL commands have been translated to Python format. However, there are a few commands that are either unsupported or are not applicable to PyMAPDL. PyMAPDL is an interactive session, so the commands that are implemented for batch mode of processing are not supported. Using these commands would not cause PyMAPDL to exit. Instead, they are ignored. Some APDL commands are not translated in PyMAPDL, as equivalent functionality is already available in Python. For example, one can use while and for loops in place of do and do while commands, and use if, elif, else statements in place of if, else if, else commands. Note that issuing these APDL commands will return an error and immediately kill the MAPDL instance. With this knowledge, now let's proceed to a workshop. Imagine a long steel pipe containing a pressurized fluid. The internal pressure exerted on the pipe causes deformation and stresses to develop in the pipe, and it may be important to understand these quantities, especially if we do not want the pipe to burst or with cyclic loading to fail due to fatigue. In this workshop, we'll perform a stress analysis of such a pipe, with the main output being the peak equivalent stress and nodal displacements developed due to the internal pressure. Due to the symmetry in the geometry and loading, we'll model only one quadrant of the geometry with a 2D plane strain formulation, which is useful for structures that are very long in a given direction. From a modeling standpoint, the geometry of the pipe is defined by inner and outer radii, and material of the pipe are assumed to be linear elastic. We fix one end of the pipe in the x direction and another in the y direction. We apply a pressure load on the inner edge of the pipe to account for the internal pressure. We'll also perform a mesh convergence study to ensure that the results are reasonably independent of the mesh density. To do this, we'll run a series of simulations with increasing mesh density and monitor the maximum stress developed in the part with respect to the number of DOFs. Once we have achieved mesh convergence, we'll use the result from the finest mesh to report the stresses and displacements developed in the pipe. To do this, we'll use PyMAPDL in setting up the FE model as a Python function and use this function to run a series of simulations in a loop and incorporate the mesh convergence study into our stress analysis. We'll start by importing all the necessary libraries in Python. In this workshop, in addition to PyMAPDL, we plan on using NumPy for working with stress data and matplotlib for plotting mesh convergence behavior. After we import the libraries, let's launch a local instance of MAPDL. Now we are ready to set up the FE model. Let us start by identifying the input parameters for this model. The material constants, Young's modulus and Poisson's ratio, geometric parameters, inner and outer radii, pressure load, and the element size are the inputs for this function. Using these as input parameters, we set up the rest of the model using all MAPDL commands in their Pythonic format. After we solve the model, we use the post-processing class to extract equivalent stresses as a NumPy array and save its maximum value to a variable max_equivalent_stress. Similarly, we save all node numbers to another NumPy array and save the size of this array to a variable num_dof that represents the number of DOFs. Finally, we return the two variables num_dof and maximum_equivalent_stress as output for this function. So we now have the FE model set up such that running this function with user inputs provides these two quantities as outputs. Note that all of the simulation data generated by MAPDL is still available, but only these two variables are extracted and saved to the Python database. Now we can proceed to perform a mesh convergence study. First, we assign values to all the input parameters. The inner and the outer radii of the pipe are set to 175 mm and 200 mm respectively. We set the pressure load to be 100 megapascals. In this example, we assume that the pipe is made of structural steel, so we define Young's modulus of 200 gigapascals and Poisson's ratio of 0.3. Next, define two empty lists to store the mesh convergence parameters. For element sizes, we define a NumPy array of 20 elements that are evenly spaced in log space. We use log space since mesh convergence is typically expected to be logarithmic. Now, we loop over this array and execute the function each time using the inputs defined earlier while changing the element size. We save results from each run and append them into the empty arrays that we defined earlier. Once all the runs are executed, we can plot the mesh convergence parameters on a semi-log plot. We can see that the maximum equivalent stress is converging to a value over log space. With this, we can now confidently report the stresses and displacements from the last analysis that are reasonably independent of the mesh density. We now plot the final mesh used, the normalized nodal displacements, and the equivalent stresses in the pipe. With that, we complete the learning objectives of this workshop. In this video, we learned how to write APDL commands in Pythonic format and work in the Python environment. We also use this to set up an FE model and perform stress analysis along with mesh convergence study. This concludes the video, and we'll continue our learning in the next video.